Assalamu alaikum. This video inshallah will be the start of chapter 9 about gas power cycles, and we will start with the ideal Otto cycle. Here we have an ideal Otto cycle has a compression ratio of 8. So we knew that it is an ideal cycle. It is not actual cycle, okay, and has a compression ratio of 8. So R is equal to 8. And for R, it is a compression ratio from its name. It is a ratio between the maximum volume over the minimum volume. The maximum volume is at the bottom dead center, okay, and we call it V1 because it is at state 1, okay, and V1, as you can see, it is equal to V4, and either you write it in volume or a specific volume, V1 equal to V4 also. And the minimum volume is at the top dead center, and it is equal to V2, and V2 equal to V3, and you can write it in the specific volume, V2 equal to V3. So the equation for R, the compression ratio, is equal to VR1 over VR2 and equal to VR4 over VR3, and we'll see what is VR. It is the relative volume, okay, and it is a dimensionless quantity, and it is located table A17. But for now, R is equal to V1 over V2, V4 equal over V3 because V4 equal to V1 and V3 equal to V2, and you can write it in the specific volume V1 over V2 and V4 over V3, the maximum volume or the maximum specific volume over the minimum volume or the minimum specific volume, and it's also equal to the bottom dead center volume over the top dead center volume. Okay, so that is for R. R equal to 8. At the beginning of the compression process, that is a new sentence. At the beginning of the compression process, what is the compression process in the Otto cycle? The compression process from 1 to 2. You decrease the volume from the maximum volume to the minimum volume. In an isentropic process, isentropic compression process, from 1 to 2, the volume is decreased from the bottom dead center to the top dead center. Isentropic means there is no heat transfer. There is no heat transfer in or out, and also means that the entropy is constant. Here in the TS diagram, S1 equal to S2. That's the process of compression is from 1 to 2. Okay. So at this process, at the beginning of this process, is state 1. Okay. So at state 1, air is at 95 kilopascal. So we have air, okay, and this air is at P1 equal to 95 kilopascal, and T1 27 degree Celsius, and is equal to in Kelvin 300 Kelvin. Okay, and a 750 kilojoule per kilogram, and when we see kilo per kilogram means per unit mass, means a small letter of heat, so it is Q small, is transferred to air. We already knew it's air during the constant volume heat addition process. Constant volume, the volume is constant. At heat addition means Qn to the system, to the cycle. Okay, where is the constant volume heat addition process in the Otto cycle? We have here heat addition Qn at a constant volume V2 equal to V3. So that is the process he is talking about. Okay, from 2 to 3. Taking into the account the variation of specific heats. So we have, as we saw in the exergy, variable specific heats and constant specific heats. Here also we have the variation of specific heat or variable specific heats and the constant specific heats. The variable specific heats, also called air standard cycle, we use for this variable specific heat assumption, table A17. Okay, table A17. In this table we have the temperature, enthalpy, relative pressure, U the specific internal energy, and VR the relative volume, and S0 is the entropy relative to the Kelvin يعني the absolute temperature in Kelvin. If you want to read about S naught, VR, PR, you can see the base from, let's write it here, base from 354 to 357, only 3 pages about VR, PR, and S naught. And if you don't want to read, okay, it is fine. It will not affect the solution or the solving of our problems. Okay. But know that the PR and VR is dimensionless quantities, dimensionless quantities. There is no unit, and VR is not the specific volume or the volume, and BR is not the pressure of يعني our pressure is in kilopascal, megapascal, but BR is dimensionless quantity and VR also. Okay. Determine. Okay, first Qn is 750 kilojoule per kilogram. Okay. At part A, determine the pressure and temperature at the end of the heat addition process. The heat addition process is here. The end of this process is state 3. So he wants to find B3 and T3. Okay. And at part B, W net, the work output from the cycle. Okay, and for C, part C, the thermal efficiency for Otto cycle. Okay, and part D, the mean effective pressure. You saw before the W net, you know about W net, the thermal efficiency, يعني W net over Qn, the famous equation, the usual equations. Okay, but what about mean effective pressure? What is the meaning of mean effective pressure? Here the work net is already the area enclosed inside the cycle, that is W net. Okay, W net, and it is also equal to the, can see say it is equal to the area also in the TS diagram, which is equal to Q net. Okay, Q net means Qn minus Q out. Okay, يعني Q, if I wrote it in small, okay, Q net equal to Qn minus Q out, and work net is equal to Wn W out minus Wn. Okay, we usually don't use this equation, and we say that W net small, يعني now I'm writing in specific per unit mass, يعني W net equal to Q net. So W net is equal to Qn minus Q out. And what is Qn and what's Q out? Qn and Q out, يعني for here, Qn is all the area under the process 2, 3. So all this area. Okay. And Q out is area under process 1 to 4. Okay. The difference between them is Q net, the area here, enclosed between the processes of the cycle. Okay. The same thing is here. You have isentropic expansion. This isentropic expansion will produce W out from the cycle. Okay, this W out is the area under the process 3 to 4. Okay, and Wn is the work in the process from 2 to 1. So that is Wn. The area enclosed is W net. The difference between the whole area, the blue one, minus the red area, will give you the enclosed area inside the cycle. Okay, we will not use this one because يعني it will take يعني in other cycles it will take some times, but يعني we will usually use this one, Qn minus Q out, and we will say W net is equal to Qn minus Q out. Okay. What about the mean effective pressure? Mean effective pressure. I removed this. The mean effective pressure, we knew that the W net is the area enclosed inside the cycle, that is W net. W net. We are searching for a pressure. If you use this pressure, okay, if you use this pressure, يعني if you multiply it by the volume change from the top dead center and the bottom dead center, this area يعني, if the volume is changed from bottom dead center to dead center, we are looking for a pressure that will give us this area in blue, which is equal to the red area enclosed inside the cycle. So we can say that the W net in blue, this area, is equal to B delta V. We are looking for a pressure. This pressure is the mean effective pressure. Okay, so this one is the mean effective pressure. If we multiply this pressure by the change in volume from BDC to TDC, we'll get a W net, which one is in blue, which is equal to the W net enclosed inside the cycle, which is this one in red. So we are looking if we have a pressure that will give me a work net during the change in volume equal to the enclosed work net inside the cycle. We are looking for this one, the mean effective pressure, because we sometimes we need something like constant يعني I can calculate it easy, in easier way يعني only a rectangle. Okay, that is the mean effective pressure. Okay, so if you see the equation for the mean effective pressure, this one is the equation for mean effective pressure. The work net over the change in volume. It is already it is a work net times the mean effective pressure times the change in volume. Work net equal to the mean effective pressure times the change in volume. If I want the mean effective pressure itself, it will be the work net over the change in volume. And in specific, يعني, this one that we will use because we have Qn in kilojoule per kilogram. And the famous or the most used one is this equation, as we will see, inshallah. Okay, let's return back to our part A. He wants me to find P3 and T3. Okay, so let's go for our equations. These equations are for the Otto cycle under variable specific heats. Okay, I want to find P3. Okay, P3 can be found from this equation. I can see P3 here, but I already don't have T3. He wants me to find T3, and also I don't have T2 or P2. Okay, how can I find P3? You cannot go directly to state 3 without finding state 2. Yani in cycles, we go step by step. We start. He gave me in the question B1 and T1. I will go first to B2, T2, then I can find B3, T3. Don't go directly and search for B3 and T3. You cannot solve this state B3 and T3 until you find the previous state, state 2. Okay. So how can I find B2 and T2? For the pressure, you will usually use the ideal gas law. Okay. يعني already what is this equation? This equation was B2 V2 over T2, and is equal to B3 V3 over T3. Okay, the volume is constant volume heat addition from 2 to 3. Okay, so V2 will cancel with V3, and we will have B2 over T2 equal to B3 over T3. And if I made a cross product, this cross multiplication, okay, it will be T3 over T2 equal to B3 over B2. So okay, I wrote the this one and ignored V2 over V3. I canceled the volume. Okay, so for any pressure, you have to use the ideal gas law. So for B2, okay, for B2, I will use also this equation. Why I use this equation exactly? Because I already have two properties at state 1, P1 and T1. Okay, I will use the P1 and T1 to find P2. Okay, but still I don't have T2. Okay, let's write this equation in terms that I want to find P2. P2 then will equal to P1 V1 over V2 times T2 over T1. I have P1 and I also have V1 over V2 because it is the compression ratio, V1 over V2, the maximum volume over the minimum volume. So I have V1 over V2 and I also have T1. The problem is in T2. Okay, so let's write P2 in terms of the compression ratio, P1 R T2 over T1. So how can I find T2? Okay, the problem is in T2. If I find T2, I can find P2. And that is a good point. You cannot find the pressure unless you have the temperature. Okay, and the pressure is not in table A17. Okay, so how can I find T2? T2, I have information that R is also equal to VR1 over VR2. Okay, if I find VR2, if I find the relative volume, I can find directly T2 because in table A17 I only need one property at that state, so I can find any other property. Okay, so if I have VR2, I can find U2, PR2, H2, T2, S02. Okay, so I need only one property. So I can, if I find VR2, I will find T2, but I don't have VR1. Okay, but VR1 is at state 1 and I have the temperature at state 1 given in the question. So let's use the temperature at 300 Kelvin and find VR1. Okay, 300 Kelvin. VR1 is 621.2 and it is a dimensionless quantity. Okay, so at T1 equal to 300 Kelvin, VR1 is equal to 621.2, and I will use the compression ratio equation, R equal to VR1 over VR2. So R, which is equal to 8 VR1 over VR2, and VR2 is equal to VR1 over R, 621.2 over 8, and this will give me VR2 77.65. Now I can find T2. Okay, so I will go to the table with VR equal to 77.65 and search for this VR. 77.65 is here between these two numbers. Okay, so I have to do interpolation, and that is a problem with the variable specific heat questions, that you usually will do interpolation in every state. Okay, so let's do interpolation between these two numbers, and we know VR2 is between them, and with the temperature, so I can find T2, which is between 670 and 680, and I will also find U. Why U? You will see later that we will need it. Okay, and usually in every state you have to find everything, yani. Okay, so let's find T and U. Okay, using the information that we know we knew VR. Okay, so let's make the table for interpolation. So I have T, U, VR. VR 78.61. My VR2 is 77.65, and the smallest value is 75.5. For U it is 488.81. I want to find U2 corresponding to my VR2 77.65, and for U also 496.62. T 670, and I want to find T2 corresponding to my VR2 680. Okay, so let's find T2. T2 is equal minus 670 over 680 minus 670 and equal to U2 also minus 488.81 over 496.62 minus 488.81, and this will equal for VR 77.65 VR2 minus 78.61 over 75.5 minus 78.61, and this will give you T2 equal to 673.087 Kelvin and U2 equal to 491.22 kilojoule per kilogram. Okay, now I have found T2. I can find P2. Okay, from this equation, B2 is equal to what? B2 is equal to 1. B1 is given in the question 95 kilopascal times R, which is 8, and T2, we got T2 673.087 over T1 300, then B2 is equal to 1705.15 kilopascal. Okay, now I got B2, I got T2. Still I want T3 in part A and B3 in part A also, but we said that before we find the temperature, we have to find the before we find the pressure, we have to find the temperature. Okay, so how can I find the temperature? Why I got U2 in the question? Because if I know U2 and I have Qn, I can find U3, right? Then from U3, I will go to table A17 and find T3. Okay, so I will write that Qn equal to U3 minus U2, then U3 is equal to Qn plus U2. Okay, Qn is given in the question 750, and I got U2 491.22. Then U3 is equal to 1241.22 kilojoule per kilogram. Okay, I will go to the table with this number, okay, and find the where it is between which two numbers. Okay, 1241.22, 124. It is between these two numbers, and I will do also interpolation. Okay, between U and I want to find T3. Okay, it will be between these two numbers, 1520 and 1540, and I will also find VR. And I told you in each set usually you will find everything. Okay, and you'll see why we need VR3. We will need it for the last part, or the part C maybe. Yes, maybe part C. Because we will need U4 in part C. Okay, so let's do the interpolation and find T3 and VR3 using the value of U3. Okay, T, U, and VR. For T, and I want to find T3, 1540. U is 1223.87, and my U3 is 1241.22, 1242.43. For VR 6.854. My VR, or the one that I want to calculate, VR3, 6.569. So let's do the interpolation. 1241.22, the internal specific energy, over 242.43 minus 1223.87, and this equal to for the temperature T3 minus 1520 over 1540 minus 1520, and this will also equal for VR3 minus 6.854 over 6.569 minus 6.854, and this will give you T3 equal to 1538.696 Kelvin, and VR3 equals 6.588. Now I have T3, so finally I can finish part A and calculate P3 from this equation. So you have T3 over T2 equal to P3 over P2. T3 we got it 1538.696, T2 also 673.087. I want to find P3, and B2 is 1705.15. So P3 is equal to 3898 kilopascal, and B3 and T3 are the maximum temperature and pressure in the Otto cycle. So as you can see, P3 is the highest one here, and temperature T3 is the highest temperature. Okay, so that is for part A. What about part B? Part B was the work net. Okay, so let's find the work net, which we said it is Qn minus Q out. Okay, what is the equation for W net? Qn minus Q out. Qn is given in the question. It is 750 kilojoule per kilogram. For Q out, I have U1. Okay, right? I have U1. I got U1 somewhere here. I got U1. I didn't find U1 but it is easy. We at the beginning we used B1 and we used T1 to find VR1, okay, and then we calculate VR2, but we didn't go and see U1. So as we said, in each state you will find everything. Okay, so VR1, so let's go to 300 Kelvin and find U1 is 214.07. So also at T1, U1 is equal to 214.07 kilojoule per kilogram. Okay, so what about U4? U4, I don't have U4, okay, but I can find U4 if I have anything that is related to this table. If I have T4, if I have H4, BR4, VR4 is not, I don't have anything at state 4. So I have to find a property at state 4 so I can find U4. And it is easier for me, and in Otto cycle we use the relative volume. Okay, we will not use the relative pressure in Otto, diesel, or either dual cycle cycles, but I think we will use it in Brighton cycle. So for Otto, diesel, and dual cycle, we will use the relative volume VR. Okay, so VR4, I need VR4. VR4 is related to R with VR3, so that is the reason I found VR3 here when we did the interpolation. Okay, so I can use VR3 with R, the compression ratio, so I can find VR4. So we will write here that VR3 or R equal to VR4 over VR3, and I have VR3 and I have R, so VR4 is equal to R VR3, and R is 8, and VR3 you got it from the interpolation is equal to 6.588. Okay, 6.588. So VR4 is equal to 52.704. And then you will go to the table again. That is the problem with the variable specific heat. You will always do interpolation. 52.704. 52.704. 52.704. Is here. Okay, 52.704 is between these two numbers, and I want to find U 500, between 560 and 576. Okay, and you will not need T4 unless he asks you in the question that find B4, then you have to calculate T4, but because it is the last state, I will not calculate T4. Okay, so we will use the interpolation between these two numbers, okay, with U. So let's write the table of interpolation. Okay, U VR 560.01, my U4 576.12, 55.54, VR4 is 52.704 and 51.664. So U4 minus 560.01 over 576.12 minus 560.01 equal to VR4 52.704 minus 55.54 over 51.64 minus 55.54. Okay, then U4 is equal to 571.5 kilojoule per kilogram. And now I can find Q out. That is the reason I need U4, so I can find Q out, and from Q out, and I have Q in, I can calculate W net, and that is for part B. Okay, so Q out is equal to U4 minus U1 equal to 571.85 minus U1 214.07, and Q out is 357.78 kilojoule per kilogram, and for W net it is equal to Q in minus Q out, and equal to 750 minus 357.78, and W net is equal to 392.22 kilojoule per kilogram. That's for part B. For part C, he needs the thermal efficiency for Otto cycle. Okay, and from the equations, the usual equation, W net over Qn. Okay, W net over Qn. W net is 392.22. Qn is 750. So the thermal efficiency is 0.523 and is equal to 52.3%. For part D, the mean effective pressure, we saw the equation for mean effective pressure. I have in the work in kilojoule per kilogram, so I will not use this one. This one is in kilojoule and this is meter cubed. And W net, I have W net, but I don't have Vmax. Vmax is the V1 and V minimum is V2. I don't have V1 or V2. Okay. But I know if I take the V1 as a common factor, it will be 1 minus 1 over R. I have R, but still I don't have V1. Okay, V1 can be calculated from the ideal gas law, and this will be the most used equations, so that is why I colored this equation in green and this also in green. You can use the ideal gas law, V1 equal to RT over RT1 over P1, and R for air is 0.287 kilopascal meter cubed per kilogram Kelvin. So the pressure here should be in kilopascal and the temperature should be in Kelvin. Okay. And you can use also this equation, but you need also to find V2 from the ideal gas. Okay, but if I have the R, the compression ratio, why not I use this equation? Okay, so I need to find V1, then I substitute in this equation so I can get the mean effective pressure. Okay, so the mean effective pressure is W net over V1 1 minus 1 over R. What is V1? V1 is equal to R T1 over B1. R is 0.287, T1 is 300 Kelvin, B1 is 95 kilopascal, so V1 is 0.9063 meter cubed per kilogram. Okay, the mean effective pressure W net is 392.22, 392.22. V1 is 0.9063 times 1 minus 1 over R, which is 8, and this will give you 494.6 kilopascal. It's a pressure. Okay, so that is for this question. We solved this question using the variable specific heat. Okay, we will use now we will solve this question also, but in constant specific heat. Okay, and we'll see what is the difference between variable and constant specific heat. Okay, so I will copy this photo. Okay, let's remove this green. Okay, I will copy this photo, and I will put it here with the constant specific heat Otto cycle. Okay, okay, it is better for me. What is the difference between Otto cycle in constant specific heat and in variable specific heat? So let's use this PDF. In Otto cycle, using variable specific heat, we use usually VR, the relative volume. Okay, here we don't have VR and we don't have table A17. So let's close this table A17. We will not use table A17. Okay, in constant specific heat, you will not use table A17 and you will not use VR. Okay, the ideal gas law is the same for both of them. Okay, the specific the compression ratio, you said there is no VR, also only V1 over V2, V4 over V3. You will not see VR. In variable specific heat, we didn't see this equation. This equation for the isentropic process. Okay, we used these equations. Okay, we didn't use them here. We find the temperatures using the table. Okay, here we find the temperatures using this equation, and you cannot use any equations that contain K, Cp, Cv with variable specific heat. Only Cv, K, Cb, this constant specific heats and constant specific heat ratio are not used with variable specific heat, only with constant specific heat. Okay, Qn and Qout. We found Qn and Qout in the using variable specific heat using U4, U1, U3, U2. So only internal specific energy. Here you will not use this internal specific energy, but rather you will use Cv delta T. Okay, you will always use Cv delta T. In the thermal efficiency, we used this one. Okay, but we didn't add this term T1 minus T2 of equal to 1 T4 minus T3. It is not here. And also we don't have this equation, the thermal efficiency of Otto cycle 1 minus 1 over R K minus 1. Here we don't have it here. We cannot use it. Why? Because there is K. This equation is derived from this equation, okay, for the isentropic. expansion under constant specific heat called air standard assumptions. Okay. CB, CV, and K are obtained from table A to A. A to A. So table 17, we will not use table 17, A17. Ignore table A17. If you want to find or to open a table, open table A2 so you can find CV, CV, and K. And usually it will be given the question in the exams, and it is easy numbers to memorize. 1.4, 0.018, 1.005. Okay. So let's go and solve the same equation but in constant specific heats. So we knew it is an ideal Otto cycle, has a compression ratio of 8, so R equal to 8. At the beginning of compression process, state 1, okay, air is at 95 kilopascal, so P1 is 95 kilopascal. T1 is 27 degrees Celsius and it is equal to 300 Kelvin. Qn is 750 kilojoule per kilogram of heat addition transferred to air during the constant volume heat addition process here from 2 to 3. At part A, he said variation here. We assume it is a constant, okay, constant specific heats. Okay, at part A, determine the pressure P3 at the end of heat addition process. Okay, and T3, the same question. At part B, W net. Part C, the thermal efficiency, and part D, the mean effective pressure. Okay. So let's see how we will find P3 and T3. Also, we have the ideal gas law. I want to find P3, but I don't have T3, and it is also required for me in part A. I don't have T2, I don't have P2. So the same start, okay? I have to find probabilities at state 2 before I find at state 3. Okay, so you can see, you can say this. I need T1. Before T1, you need T2. Before T2, you need T1, and before T3, you need T2. Okay, and before T2, and also if you need B3, and before B3, you need B2, and before B2, you need B2 T2. Okay, to be clear, you have to find temperature before pressure. Okay, and you have to find the state, the state 2 and 1 before you find 3, and you need to find 3 before you find 4. Go step by step. Okay. I have also B1. Okay. How can I get T2, T3, and B2 so I can find B3? For B2, we'll use also the same equation. Okay. I have P1, T1, and I will say V1 over V2 is equal to R. So B2 is equal to P1, V1 over V2, T2 over T1. I have V1 over V2 because it is the compression ratio. But the problem also is T2. How can I find T2? In the previous question with variable specific heat, we used table A17. Here we used the isentropic relations. And find it from here. So T2 is here in this term, this side. Okay, I can use it with either of these equations. The easiest one is R. R is V1 over V2, and also it is V4 over V3. So I will say that T2 over T1 is equal to R K minus 1. Okay, and T2 is then equal T1 R K minus 1. K is 1.4 from table A17. Air 1.4. Okay, so T1 is given in the question 300 Kelvin. Put it in Kelvin. Okay, R is 8, K 1.4 minus 1. So T2 is equal. T2 is 689.22 Kelvin. Okay, I found T2. And now let's find B2 from this equation. This one, B2 is equal to B1 95 kilopascal, R 8, T2 is 689.22, T1 is given in the question 300 Kelvin, or I converted to Kelvin. You have to put it in Kelvin. Okay. B2 is 1746.024 kilopascal. Okay. So also I found B2. Still T3. Okay. T3 I can use also this equation, but I don't have T4. So how can I find T3? In the previous question with variable specific heat, we found U2, then we use Qn equal to U3, use Qn equal to U3 minus U2, and we found U2 from T2, and then Qn and U2 I already have them in the question, so I got U3, and from U3 I found T3. Here the same thing, but with temperature, with not internal energy. I will use this equation, Qn, I have Qn, I found T2, CV from the table, I can find T3, okay? So let's write Qn equal to CV T3 minus T2. Qn is 750. CV from the table A2A, 0.712, 0.718, 0.718. Okay, T3, I want to find T3. T2, I already got it here, 689.22. So T3 is equal to 1733.79 Kelvin. Okay, and finally I can finish part A and find B3. Okay, I have B1 and T1. I found T2. From T2 I got B2. Then I found T3. From T3 I got B3. Okay, so T3 over T2 equal to B3 over B2. Then T3 is 1733.79 over T2, 689.22 equal to P3, 1746.024. So P3 will equal to 4392.27 kilopascal. A big number because it is the highest pressure, the maximum pressure in the cycle. Okay, so I finished part A. What about part B? Part B, the W net equal to Qn minus Q out. Okay, Qn, I have Qn. What about Q out? Q out is equal to CV T4 minus T1. I have T1, CV. I knew it from the table. What about T4? T4. If I use the ideal gas law, I already don't have P4. Okay, I cannot use this one. So let's go to the isentropic relations. We said in variable specific heats we use tables to find temperatures. Here we use the isentropic relations to find the temperatures also, but in constant specific heats. Okay, so for constant specific heats I will use this equation. You can see here it is I have T3, okay, and I want to find T4 and I have R. Okay, so let's use this equation. T3 over T4 equal to R K minus 1. So T4 is equal to T3 R K minus 1. T3 is 1733.79, 8 power 1.4 minus 1. So T4 is equal to 754.68 Kelvin. And then Q out is equal to CV T4 minus T1. CV from the table is 0.718. T4 is 754.68 minus 300 Kelvin T1, and then Q out is equal to 326.46 kilojoule per kilogram. Okay, and finally W net will equal Qn minus Q out. Qn is 750, Q out 326.46. Then W net is 423.54 kilojoule per kilogram, and that is for part B. For part C, the thermal efficiency for Otto cycle, you can use any of these equations. Okay, W net over Qn, 1 minus T1 over T2, 1 minus T4 over T3, this new equation. So let's solve with all of them and see if the number will be the same or no. Okay, because they are already derived from each other. Okay, of course they will give you the same equation. Okay, and you cannot use this equation that contains K with variable specific heat, and you cannot use T1 over T2, T4 over T3, 1 minus T1 over T2, 1 minus T4 over T3 with variable specific heat. Just use with variable specific heat W net over Qn, 1 minus Q out over Qn, these terms, but don't use the one written in the constant specific heat. Okay, so let's find the thermal efficiency. W net over Qn. W net is 423.54 over 750, and this will give you 0.564. Actually it is 0.565, but in solution manner they put it 0.564. Okay, equal to 6.4%. Let's use the other equation. 1 minus 1 over r k minus 1, it will equal 1 over 8, 1.4 minus 1, and also will give you the same number, 56.4%. And also thermal efficiency, Otto cycle, 1 minus T1 over T2 give you 1 minus 300 over 689.22 equal to 0.564 equal to 56.4%. And finally Otto cycle, 1 minus T4 over T3, 1 minus 754.68 over 1733.79 also will equal the same number, 564, 56.4%. Okay, for part D, the mean effective pressure, we already saw from the last question, W net equal to V1, 1 minus 1 over R. Okay, and V1 is equal to R T1 over P1. R is 0.287 times 300 Kelvin over P1, 95, and V1, the same number from the last question, 0.9063 meter cubed per kilogram. W net is 423.54. V1 is 0.9063, 1 minus 1 over 8, and this will give you 534.09 kilopascal. Okay, so that is for this question with the constant specific heats. Okay, so what if the question didn't give me Qn in kilojoule per kilogram but in kilojoule? So I will use these equations, Qn equal to mcv T3, only the mass is the addition. So how can I find the mass if it is given, يعني I need it in the question? You can also use the ideal gas law, the ideal gas law, M equal to B1 V1 over RT1 or with any state. Okay. What else? If he asks you about the Carnot cycle, compare your efficiency with the Carnot cycle, so you'll use 1 minus TL over TH. TL the lowest temperature and TH the highest temperature. The lowest temperature is 1, the highest temperature is 3. What else? Okay, let's compare the values from between cold air standard assumption and various standard assumption or air standard cycle. W net for this one 392.22. Our W net from the constant specific heat was 423.54 kilojoule per kilogram. So it is higher here. The mean effective pressure for the constant was 534.09. The thermal efficiency was 56.4%. Okay, of course B1 and T1 will be different. So you can use either depend on the question if you said constant or variable. Okay, and if it didn't mention anything, you have to assume. Okay, variable is harder, or you can say harder, but it is longer because there is a lot of interpolations. And variable, but on the other hand, variable is more accurate. Okay, variable is more accurate than the constant specific heat. You can say that constant specific heat is overestimated, or it will give you an error but in positive. Okay, you can see work net is higher, efficiency is higher, mean effective pressure is higher in constant specific heat, but the accurate one is the variable specific heat. Okay, but it is longer, it has a lot of interpolations. Okay, that is for this video, and this video is only about ideal Otto cycle. Okay, we will have another video inshallah about actual Otto cycle. When we have actual Otto cycle, means that we have isentropic efficiency. We will see inshallah in the next video inshallah.